Traditional financial modeling relies on fixed inputs to yield a single, predictable outcome. If revenue grows at 5% and costs grow at 3%, a standard valuation model will always compute the exact same result. This graphic illustrates the deterministic approach. We plug in fixed input values, like a flat 8% discount rate, and generate a single, rigid output, in this case, exactly $100 million. But financial reality does not move in isolated, straight lines. When stress events hit, these fixed assumptions shatter. Relying strictly on an expected value or a mean return creates a dangerous blind spot for decision-making. Two portfolios can share the exact same average expected loss, but one might have a massive concentration of extreme downside exposure hidden beneath that average. Executives and risk managers do not survive by managing to the average. They are forced to operate in the extremes, navigating threshold breaches and tail risks. This side of the chart shows stochastic modeling, where inputs are treated as random variables. Instead of one fixed number, we generate a wide distribution of results, mapping out the best-case scenarios against the severe downside risks. Monte Carlo simulation requires a structural shift in how an institution analyzes risk. It stops asking the unanswerable question, what exactly will happen, and instead asks, what is the full distribution of possible states, and how likely is each one? Survival in modern finance requires abandoning static predictions. Instead, we have to mathematically engineer a structured map of uncertainty. The first step in building that map is redefining randomness. In common conversation, randomness implies chaos, disorder, or a complete lack of pattern. This diagram corrects that misconception. In statistical modeling, a random variable is simply one whose exact realized value cannot be predicted in advance. However, its aggregate behavior still respects a defined, stable probability structure with a measurable mean and variance. To capture that behavior, we assign specific mathematical shapes, known as distributional assumptions, to our uncertain variables. This dictates how often extreme events occur versus everyday fluctuations. Relying on the normal distribution is a critical trap. Assuming symmetrical returns ignores reality. Markets exhibit skewness and fat tails. We must select distributions that fit actual mechanics, like log normal for non-negative asset prices, or bounded beta distributions for debt recovery rates. Once the mathematical shape is chosen, the engine needs data to calibrate it. This introduces the mechanics of statistical sampling. This chart separates two distinct sampling layers. Layer 1 uses historical data to estimate parameters like volatility or default frequency. Layer 2 takes those parameters and generates thousands of simulated draws, creating a synthetic representation of future states. If you pull your Layer 1 historical data from a low-interest rate bull market and use it to model risk in a high-inflation environment, you introduce structural bias. 10,000 synthetic iterations of a flawed baseline will only multiply the error. A Monte Carlo engine is only as strong as its underlying assumptions. Mathematically elegant distributions built on biased historical samples will yield precise, well-formatted, and highly dangerous lies. Beyond isolated variables, the engine must handle how modern financial products actually behave. Instruments like option payoffs, covenant-triggered debt, and complex liquidity gaps exhibit nonlinear behavior. This compares the simplistic straight line of traditional sensitivity analysis against real-world nonlinearity. In a linear model, doubling an input shock doubles the loss. In reality, a small change might have zero effect until it hits a specific threshold, where losses accelerate exponentially. Variables don't just behave non-linearly on their own. In a true stress event, disparate risks across a portfolio cluster and trigger simultaneously. Look at this map of complex banking risks. A loan portfolio suffers when defaults cluster. Probability of default and cross-borrower dependence feed into total loss. Across market risk and asset liability management, we see the exact same pattern merging into a single system. Monte Carlo simulation handles this complexity by forcing variables to move jointly across sequential time paths. It evaluates how a sudden spike in interest rates might simultaneously crush collateral value, trigger a wave of corporate defaults, and accelerate deposit withdrawals. Real-world financial devastation is born from correlation and compounding nonlinear events. Only a multivariate stochastic model is mathematically equipped to reveal these hidden systemic vulnerabilities. Theoretical randomness has zero practical value until it's hard linked to an institution's specific balance sheet mechanics. This diagram outlines the three-tiered software execution architecture required to build a functional, reliable stochastic engine at scale. The foundation is Microsoft Excel. It provides visible cash flow construction and transparent deterministic skeletons. Analysts can audit the formulas and interact directly with the baseline financial logic. Excel alone bottlenecks at scale. Clicking recalculate 10,000 times is not a viable strategy. The model requires an automation layer. VBA handles the computational lifting, executing custom random sampling and automating scenario cycling without manual intervention. This graphic highlights a critical safeguard: strict model architecture. If structural inputs are not cleanly separated from the underlying calculations, the workbook will become fragile and degrade over time. Controlled random generation must be isolated from the reporting outputs. Once executed, the VBA layer produces millions of raw, tabular simulation iterations. But a spreadsheet with a million rows of synthetic market states is practically useless without translation. Power BI serves as the governance layer. It translates raw data into actionable breach probabilities, tail loss dashboards, and interactive percentile views. Together, this integrated tech stack converts theoretical mathematical iteration into a governed, auditable pipeline built specifically for executive decision-making. We have to issue a critical professional caveat. A simulation is a disciplined map of assumptions. It is not a crystal ball that discovers absolute truth. This chart illustrates the model's boundary. On reduction left, we have measurable aleatory uncertainty, like daily market movements. On the right, we have epistemic uncertainty, deep ignorance where historical data loses relevance, facing structural breaks, market dysfunctions, and geopolitical shocks. A polished Power BI dashboard must never create false comfort. It cannot serve as a substitute for human economic judgment during sudden, out-of-sample crises. The ultimate purpose of Monte Carlo output is not to produce an elegant chart. Its sole purpose is to compel a definitive governance response. If the model reveals a 10% probability of a liquidity breach, the institution must act. It means altering capital buffers, modifying liquidity strategies, or rejecting projects with unacceptable tail risk. Monte Carlo simulation is an essential operating philosophy. It maps the mechanics of uncertainty and locks it down into a structured, governable asset.